Good morning, everyone. Today we will have our session 6 on linear systems. So far, we have used this Bash-Lack operator, just maybe without thinking too much, to solve the linear system AT equal B. And it's a very efficient way of doing things actually in MATLAB. But we want to know how this actually operation of this Bash-Lack operator or a lead analogous methods, how do they work? What is the essence about those methods? So let's talk about it. Before starting, I wanted also to point out that there is no such a thing as solving a nonlinear system by itself. So the solution of a nonlinear system is composed by most of the time iterative methods of linear systems. So at the end of the day, solving a nonlinear system is equivalent to solving several times a linear system, for example, the Newton-Raphson method. And we will realize today that solving a linear system is basically carrying out some algorithms where matrix vector multiplications are taking place. So at the end of the day, CFD is just how to do matrix vector multiplications to solve a given fluid dynamic problem. So this is the summary. We have finite differences already. We did also finite volumes. We did unsteady simulations on finite volumes. And we will do next time Green's functions. So today we are in how to solve linear systems. And you will see that actually we want to first express these linear systems as sparse linear systems to make the operations more efficient. So what is this slide about? You may think that I'm showing you like sort of piece of art to be hung out at someone's home. And maybe good for that purpose. But actually what we are watching here is just a matrix A. So the same matrix we had in our course, but maybe more complex. In here we can see that there are many things happening. And when you look at this somehow picture, you can realize what is going on maybe. So you already have, for example, these three squares in here. So you may already imagine you have here a vector multiplying this matrix, and there are vectors that are related by these relations. Another piece of the vector being satisfied with this one, and another one by this one. So we have like three kind of systems of equations. So maybe we have three kind of variables. Who knows? Also, we realize that these squares in here represent the coupling, how these variables are coupled, this one from this one and these ones to these ones. And you can also realize that at a given point, for example, this black line, all of them are connected. So you can see that by looking at the structure of a matrix, in this case, let's call it A, you can realize maybe what is going on in the system of equations, okay? Our case is a little bit more simple. So our case is more simple. So if we just place ourselves in one row of this square, you will realize we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 nodes connected. And that can be actually referring to the finite volumes scheme when we have P and all the surrounding nodes. When we just increase the size of the mesh, so you will see that the number of non-zero elements in this matrix A increases. So the idea is to make sense of this amount of zeros. So when we have a matrix that has a very low density, like this one in here, we want to make use of this sparsity of the matrix, and this is what we'll just discuss. So we just saw that we have a square matrix. So basically we have n to the square number of elements in this matrix, and we have to store them, of course, but actually it makes more sense if we store only the non-zero elements. So that's why if we actually aim at the, say, naive approach of storing the whole stuff, then we will have that the storage is scaling as n to the square. But if we are smart, then and we just store the non-zero elements, so you just saw that the matrix is like a sort of diagonal, more of one diagonal with some of diagonals. Then you will have that when the system increases, so you increase the number of the cells in your mesh, the storage will just increase with n to the power of 1. So this is a very strong difference that we have to consider in storage, but not only in storage but also in terms of computational power. If we, for example, just make use of Gaussian elimination, so there is like a well-established number of steps to be able to solve the linear system, and if we have a matrix with n elements at the side, so we have a n times n A matrix, we will have to perform n to the cube number of operations to be able to obtain the final answer. And we are maybe doing something silly like many operations, like a given number times 0. So we already know the answer is going to be 0, but still we are doing the operation, and this is actually a waste of computational power. Therefore, if we use the sparse format, those operations, something times 0, are completely avoided because we already know the answer. And if we use still the same method, Gaussian elimination, we will have that the number of operations required is just scales as n to the power of c. Well, this depends actually on the sort of system. So if the system is it presents a very low density, so we can have like n to the power of 1, so almost like scales linearly. However, if the matrix is super dense, so that there are very few zero elements, then the number of operations required will be almost close to this one, so there wouldn't be much gain. But most of the time in CFD we have that this connection between neighbors, and therefore these kind of diagonal matrices like showing up, and therefore having this sparse format is going to be very useful as well, so for both storage and for the corresponding mathematical operation we are interested in. So we just talked a bit about this Gaussian elimination, which is a direct solver. So you already know from the beginning the number of operations you have to perform to obtain a given answer, a given result. Now, what happens if we, instead of direct solvers, as this one, we just use the so-called iterative solvers? So an iterative solvers, we're not aiming at a very accurate answer, but we are aiming at an answer that we had with a given residual or a given tolerance that we are happy with. So basically, the nice thing of iterative solver is that at every iteration you are approaching the actual truth, but you can stop before achieving the truth, because you will have an approximation that is already satisfactory. When you use the direct solver, you have to wait until the end, because in between there is nothing as a result getting closer to the truth, so you have to wait until the end. So these iterative solvers is what actually is are ubiquitous in CFD. Something else is that iterative solvers, they exploit the fact that almost most of the time in CFD matrix are sparse. So if we have, and this is something you will realize today, if we have a dense matrix and we want to use iterative solvers, that actually is gonna be not a very good idea. Maybe your system, your algorithm will not actually converge, and in that sense you will have to use a direct solver. Okay. There is an additional requirement when using iterative solvers, and we will see that that requirement is the use of preconditioning. If we do not use preconditioning, we will have a very hard time converging to a given result. Actually, you can eventually converge, but it will take ages because your matrix A is not well conditioned. Then if you somehow precondition the matrix A, so improve the conditioning, things will be behaving much better. Okay, and in that sense, then the advantage against direct solvers actually show up. So what is preconditioning? Preconditioning is just multiplying a given matrix, here denoted with C inverse, and you will see that this is going to be a matrix, this is going to be a vector, so we will have a different system, but the answer, so the answer that we're interested in, this x vector, is going to be the same. So different problem, same solution, and we're interested in having this matrix A being very better conditioning. So what is actually something that is ill conditioned? Something that is ill conditioned is something, or in terms of matrices, a matrix that is very close to be singular. When you have a singular matrix, or a matrix that is very close to be singular, any perturbation in A or this vector B will produce a completely different solution X. And this is something we don't want to have because we are solving an iterative algorithm. We have already a number of steps that we want to follow iteratively. And if we have this high sensitivity to perturbations in B or in A, then maybe we will have trouble in converging. Now, if we just multiply and we just consider a good matrix C, this conditioning of the matrix will actually improve a lot, and therefore the sensitivity to changes in A or B will not completely influence or will not influence strongly this solution X, and therefore the convergence to the actual truth is going to be much smoother, and we will eventually obtain a result. So now the question is how to obtain this C, this preconditioner. We'll see that in a couple of slides. First, let's go to the Richardson iteration. So this is a very interesting algorithm which actually deliver results. So let's assume at the beginning we need an initial condition. So we need to have an initial guess value, which is going to be called here x0. And then we will just have this residual b minus ax. So of course, since this is a guess, this cannot be 0. This is a residual. But then you have this residual, and you add the residual to your initial guess, and you obtain like a second guess. Let's call it like that. And then we repeat again into the while loop until this residual goes and goes smaller. If you do this, maybe things work if the matrix A itself is well preconditioned, but most of the time it's not. So we just add now the preconditioning matrix in this step, Voila, we have here this matrix C, and you will see that depending on how the, or let's say the characteristics of this matrix C, this loop will maybe have a very few amount of steps, or maybe it will not converge at all, depending on this C. The nice thing also of this Richardson iteration is that is it possible to know if we will converge or not before doing the actual computation, and this is done in the following way. So we just define an error, which is going to be the guess at the step n plus 1, so this is the guess x at n plus 1, minus the truth. So let's assume this is the truth, so this is gonna be the error in between. Then we just perform the operations in here, we obtain this. So just be aware that xm minus x star is error m here, and this is nothing but this. So basically we can just relate the error at step m with the error at step m plus 1. That's a very nice thing. So we have just this thing in between, this somehow transformation matrix that we will call T. So if we know what T is, or the characteristics of T, we will know if our loop or our iteration is going to be convergent or not. So we have to evaluate T, and remember that T is a matrix. So let's write this thing in terms of an eigenvalue problem. So we have T, an eigenvector, equal lambda and the eigenvectors. So this is an eigenvalue problem, a linear eigenvalue problem. And you can see that V and lambda are the eigenvalues and eigenvectors of this matrix T. So what is this important about? So remember that what a matrix does, a matrix is something that performs some transformation on a given vector. So we have a T and we have a Z here. This is just a given example, and then we consider this is gonna be what Y. So Z is gonna be dilated, maybe it's gonna be compressed, maybe it's gonna be rotated, and we're interested right now in how this matrix is able to dilate, so to dilatate this Z vector. So in order to understand these dilatation coefficients, we will have to understand these eigenvalues. So let's assume we perform this eigenvalue problem and we obtain a given amount of eigenvalues. One of the eigenvalues, let's say the maximum one, is equal, so the largest one is going to be equal to lambda equal to 3. This is just to say something. So what does it mean? That if you have the vector z, and if the vector z happens to be very close to this eigenvector v, it means that the matrix T will not create maybe not a strong rotation, but basically a dilatation. So this vector z is gonna grow 3 times and become y. Now when z is far away from b, okay, maybe this growth, so the dilatation of z of 3 times to become y will not happen. Maybe you will have another effect. So this dilatation only happens when z is equal to or very close to v. And this is what we call maybe the worst scenario, how large, how much this z can be enlarged. And this is given by the maximum eigenvalue, in this case 3. If lambda is actually smaller than 1, if the maximum eigenvalue is smaller than 1, then we are happy because we will know, at least for our purpose, that z cannot ever grow under that matrix T. So grow in terms of dilatation. So dilatation, I'm using these two words as synonyms. So we can now state that we need that the absolute value of all eigenvalues of t, they must be smaller than 1, so that we assure that the error will always be decreasing and not increasing. So this is something you will have to take into account today. So I have by experience that there are groups that they just work and on a given iterative scheme, and you realize that everything exploding but you don't know why, and then you keep trying something that by definition wouldn't work ever. So what you have to do when you just create and you just define your preconditioning matrix, which is this C, then you just compute T, you compute the eigenvalues. So in other words, this is also the spectral radius, and that you just see that the absolute value of the maximum eigenvalue is smaller than 1. When that happens, then you say, okay, this iterative algorithm should converge, then I will just put my effort in making it right, correctly. But if it gives you that it is gonna be, there is an eigenvalue that is larger than 1, the absolute value, then I mean, why just to try to solve this? This is gonna be divergent at some point. Okay, so just be aware about this fact. Okay, so now while we were maybe waiting for what is this preconditioning matrix C? The thing we wanted to know maybe from already some slides ago. Basically, the best preconditioning matrix ever is the one that produces the product of C inverse times A being the identity. So actually something like this. So the conditioning number of the identity matrix is 1. So this is the lowest it can be, which is great. But now, for that, C has to be actually what? A. So, and then we will need to compute the inverse of A to carry out this multiplication, which basically what we are doing is solving the problem. And then we need to solve the problem in order to solve the problem. So there is not like a real consistent story there. But what we learn from this is that, okay, maybe we cannot have C being exactly A, but we can obtain the most important parts of A to construct the preconditioning matrix. And therefore, this decomposition is done of the matrix A. Let me just... And the easy one is when we consider just the diagonal elements of A to compute the preconditioning matrix C. And this is going to be called the Jacobi iteration method. So when we apply the Richardson iteration on this definition of the preconditioning matrix C. So C is going to be equal to D. And then we have the Gauss-Seidel when we consider just D and the lower part of the matrix A, E. And this is going to be now called Gauss-Seidel method. If we just include a relaxation factor, that is like a kind of factor to make the Gauss-Seidel converge faster, but at the expense of maybe blowing up the method. So we can actually regulate this omega to customize the convergence speed if you want. So this is the SOR method, the successive over relaxation method. So if we apply the Jacobi iteration in here, so this is the Richardson iteration, so we have to give to this loop, or to this for loop, this quantity. And what is this? So having the inverse of a diagonal matrix is super simple, because we just need to have 1 over d. It's a diagonal matrix. So this is simpler, and this Jacobi algorithm you will be computed in MATLAB, and you will realize that just using matrix vector multiplications is enough to assess the final value of x that you desire. But I don't want to tell much. The idea is that you create your own algorithm. Now, what happens when we want to use instead the Gauss-Seidel iteration, for example? Then this is what we obtain. And computing this is not straightforward, so you cannot do 1 over t plus e. I mean, this is wrong, okay? Because this is not a diagonal matrix anymore. Then we could eventually, for the class of today, I mean, we could, but we will not do it, use the inverse function of d plus e, and just introduce here the actual inverse of d, so the inverse of d plus e, and compute the whole Richardson iteration, okay? But we will opt for a better method, and you will see that this is going to be very interesting, how we are able to solve this equation without actually computing the inverse of d plus e. And this is something I will explain right now. So something that is important, that you have to do it, and I hope you do it like right now, just to be in the mood. We have to convert this matrix, this expression, reorganize it in such a way that we obtain this expression, okay? So please try to do this exercise. Just consider that a can be split in d plus e plus f, remember. If you don't get it, we just can be like chatting on MS Teams, but this is important, okay, for the exercise of today. Okay, but now let's assume that you succeeded reorganizing the expression to obtain this one, and this is the starting point. When you look at this, you say, okay, I don't have any inverse matrix as d plus e. I mean, we have here the inverse of d, but this is easy, so it does not matter. This is 1 over d. But the first question you may have is, how on earth can I solve this if I have the output also both at the left and the right hand side? So this is solvable actually? And the interesting question is yes, if we look at the structure of the problem. So let me just explain what we have here. So we have the node, the vector xm, as with this light green. This xm plus 1, it doesn't somehow represent this, so forget about this for this moment. And xm plus 1 is going to be an orange one, but in this vector it shares, so it's like the first element actually belongs to xm plus 1, but the other elements, they belong to xm. In addition, we have the lower part of the matrix A, which is this blue one, and the upper part, which is this F. So they do not contain the diagonal, just see this. And we have also with this dot in here, it's just somehow showing what is the element we are actually considering in this 1 over d, okay? And we will compute xm plus 1 row by row. Now let's start. So the first thing is we start in the first element, 1 over d, so we consider this element 1 over d. The matrix, the vector b is going to be always the same. and then we need to multiply xn plus 1, but we don't have xn plus 1. But now let's assume if you had xn plus 1, you multiplied it by a row of zeros, which at the end of the day is going to be 0. So it doesn't matter that we don't have xn plus 1, because this dot product is going to be 0 and it will not contribute to the sum at the first row. And in here we will just, everything is xm is going to be multiplied by this row of f, which is actually non-zero, so it contributes, and that sum is going to give me the first element of xm plus 1. If we continue, then we will consider the second diagonal element here, 1 over this element. We go in the second row now, and now we do need to have xn plus 1. Fortunately, for the previous iteration, we already have the first element of this x matrix is going to be, x vector is going to be xn plus 1, and this is going to be multiplied by the only non-zero element in here, which is this blue element, and the rest that we don't have it, we don't need it, because this is going to be also multiplied by 0. In the same way in here, this xn plus 1 it will be wrong, but this is going to be multiplied by 0 anyway, so it doesn't matter, and the rest is going to be xm, and this is going to be multiplied by this row, the red, with red elements, and this multiplication will give us the second element in xm. Okay, and we can go, so again here we have two elements of xm plus 1, the only ones we have, but these are the only ones we need to multiply to these two in here, and this one multiply the actual red elements in here. So you just saw that we can do that. We can go element by element until completing the whole computation of xn plus 1. Okay, so please, I want you to do this today in this way. So I don't know what to have the Gauss-Seidel approach just by computing the inverse of d plus e with a command of MATLAB. Okay, the idea is that what we learned today can be extrapolated to any kind of program. So it doesn't have to be MATLAB, it can be something that very low level, when you don't have these functions that as inverse or something like that, and then just by using matrix vector multiplications that can be actually built by for loops in those cases, then you obtain the solution of your linear system. Okay, so this is the purpose of today's exercise. Okay, so this is the last slide. Thank you very much again for your attention, and we will discuss the exercise during the lecture on Friday. Okay, bye bye.